پروف یا اثبات این قضیه رو مرور میکنیم. Let fx is not zero for some number c in the interval a to b. Let fx is not zero for some number c in the interval a to b. Without laws of generality, let us assume that if c is greater than 0. Okay, if c is greater than 0. This is assumption. Now, because of continuity of f, we have fx is greater than 0 for some interval x1 to x2. Okay, again, since fc is greater than 0 and the function f is continuous for interval x1 to x2, we have also fx is greater than 0. Okay, now let gx is equal to x minus x1 times x2 minus x for x in the interval x1 to x2, and gx is 0 outside this interval. Okay, not that x minus x1 times x2 minus x is positive for x in the interval x1 to x2. اوکی، به راحتی میتونیم چک بکنیم که تابع x منهای x1 ضرب در x2 منهای x پوزیتیو یا مثبت توی این بازه. خب now consider integral from a to b fx gx dx is equal to، این انتگرال رو تقسیم بازه میکنیم. تقسیم بازه آتابی رو برای این انتگرال تقسیم میکنیم، مساوی میشه با انتگرال از آ تا x1 fx gx به اضافه انتگرال از x1 تا x2 fx gx به اضافه انتگرال از x2 تا b fx gx. اوکی، پس چون بازه ما به این صورت بود که بازه کلی آتابیه و x1 و x2 هم درون بازه آتابی قرار دارن، تقسیم میکنیم انتگرال از آ تا x1 به اضافه انتگرال x1 تا x2 به اضافه انتگرال x2 تا b. خب انتگرال اول و آخری برابر با چی هن؟ صفرن. چرا؟ این خاطر که ما توی این دوتا بازه gx رو صفر تعریف کردیم. در بازه آ تا x1 و x2 تا b تابع gx رو صفر تعریف کردیم. پس این دوتا انتگرال چی میشن؟ صفر میشن، اولی و آخری. پس این مساوی میشه با انتگرال از x1 تا x2 fx gx dx. اوکی، حالا باز x1 تا x2 gx تعریفش معلومه. مساوی میشه با انتگرال از x1 تا x2 f(x) ضرب در x من x1 در x2 من x dx که این بزرگتر از صفره. خب این انتگرال چیه؟ بزرگتر از صفر. خب چرا بزرگتر از صفره؟ علت بزرگتر از صفر بودنش چیه؟ این انتگرال اولا فرض کردیم که f(x) بزرگتر از صفر تو این بازه. ثانیا اینجا هم فرض کردیم که x من x1 در x2 منهای x هم چیه؟ پوزیتیوه. این دوتا با هم دیگه نتیجه میدن که این تابع چیه؟ حاصل این انتگرال بزرگتر از صفر. نتیجه what's the result? Thus we get a contradiction to what is given in the lemma. Okay? If we assume f(x) is not 0, then we get a contradiction. This implies that f(x) is equal to 0 on the interval a to b. And the proof is completed. خب بعد از این قضیه میام سراغ Euler Lagrange equation. Okay? Euler Lagrange equation or necessary condition for extremum. Okay? توی این قسمت میخوایم necessary condition for extremum رو برای calculus of variation بررسی بکنیم. طبق این صورته if y(x) is an extremizing function for the following problem. If y(x) is an extremizing means minimizing or maximizing function. One of them. Minimizing or maximizing. If y(x) is an extremizing function for the problem. What's the problem? Minimize or maximize iy is equal to integral from x1 to x2 f x y prime dx with n conditions yx1 is equal to y1 and yx2 is equal to y2. This is the simplest form of calculus of variation problems. The simplest form of calculus of variation problem. Then yx satisfies the BVP. What is BVP? BVP is the abbreviation of boundary value problem. Boundary value problem. Oliver? Problem. مثلا به بانداری ولی پروبلم یا بی وی پی به این صورت میشه دی به دی ایکس روند اف به روند وای پریم منهای روند اف به روند وای مساوی با صفر با همون دوتا شرط نهایی که داشتیم بالا. وای اکس یک مساوی با وای یک و وای اکس دو مساوی با وای دو. این معادله رو ما بهش میگیم اویلر لاگرانژ اکویشن. اویلر لاگرانژ اکویشن و این اویلر لاگرانژ اکویشن برای حل مسئله حساب تغییرات استفاده میشه. اوکی؟ برای حل مسئله حساب تغییرات ما از این اویلر لاگرانژ اکویشن استفاده میکنیم تا اونو تبدیل کنیم به یک بی وی پی. با حل کردن این بی وی پی میتونیم تابع وای ایکس رو به دست بیاریم. Okay, let me again explain in English. For solving a calculus of variation problem, we first use the Euler-Lagrange equation to obtain a BVP. Then, by solving this BVP, the solution yx can be obtained. This is the solution method. خب این قضیه اثباتش خودخوان میذاریم. یعنی اثبات قضیه اجباری نیست. خب پس اثبات این قضیه اویلر لاگرانژ رو خودتون مطالعه کنید. مستر احمد، این برهان که disproof is not necessary. Okay, غیر مطلوب. But study this proof. Study this proof, and maybe you need it in some practices. Okay, study this proof, and in some practices you may need this proof. Okay, so try to understand this proof. So مجددا اون معادله اویلر لاگرانژی که ما نیاز داریم به این صورت بود، یعنی دی به دی ایکس راند اف راند وای پریم منهای راند اف راند وای مساویه با صفر. خب این قسمت برای ما مهمه. Different forms of Lagrange equation. Different forms of Euler-Lagrange equation. خب به عنوان یکی دیگه از فرم های معادله اویلر-لاگرانژ این قسمت رو در نظر میگیریم. Suppose that yx is an extremizer of iy. Okay. Since f is equal to fxy and y prime, which means that f is a function of x, y, and y prime. Then d over dx of f, d over dx of f is equal to round f over round x times dx over dx plus round f over round y times dy over dx plus round f over round y prime times dy prime over dx. Okay? And if we simplify it, اگر سادش کنیم دست میاریم روند f به روند x، چون میدونید که این dx 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 به dx برابر با چیه؟ برابر با یکه. این dy به dx میشه y پریم و dy پریم به dx میشه y زبون. پس ساده شدهش میشه روند f به روند x به اضافه روند f به روند y ضرب در y پریم به اضافه روند f به روند y پریم ضرب در y. خب. Now consider d over dx y prime times round f over round y prime is equal to y prime times d over dx round f over round y prime plus round f over round y prime times y is equal. Okay? The second derivative of y. Subtracting 4 from 5. Okay? Subtracting let me check 5. Subtracting 5 from 4, we get df over dx minus d over dx y prime times round f over round y prime. It will be equal to round f over round x plus round f over round y times y prime minus d over dx times round f over round y prime times y prime. Okay? Subtracting 4 minus 5 produces this result. Consequently, we obtain d over dx of the function f minus y prime times round f over round y prime minus round f over round x is equal to y prime times round f over round y minus d over dx round f over round y prime. Now, we know that this part is equal to 0. Okay? Round round f over round y minus d over dx round f over round y prime is equal to 0. This is Euler-Lagrange equation. This part is Euler-Lagrange equation. خب نتیجه چیه؟ What's the result? As yx is an extremizer and by using Euler-Lagrange equation we get d over dx of the function f minus y prime round f over round y prime minus round f over round x is equal to 0. Which is another form of Euler-Lagrange equation. This is another form of Euler-Lagrange equation. بنابراین معادله اویلر-لاگرانژ رو برای به دست آوردن جواب الان دو تا فرم براش بلدیم. We now have two different forms for Euler-Lagrange equations. No, Mr. Mana. Both of them, which means the one at the top of the page is a form of Euler-Lagrange equation, which is also a BVP. The first form and the second form both will produce a BVP. Okay? These are two different forms of Euler-Lagrange equations, and both of them produce a BVP. And by solving the obtained BVP, we can find the solution Yx. اوکی بچه قبل از اینکه اسپیشال کیسز رو چک بکنیم before going to special cases یک مثال بررسی بکنیم. خب یه لحظه اوکی بذارین let's continue and check special cases. Let's continue and check special cases and then we solve some examples, okay? Then solve some examples. Okay. این اکسترمایزر پرابلم رو در نظر بگیرین. Consider this as problem. Extremize Iy is equal to integral from x1 to x2 f xy prime dx with boundary conditions yx1 equal to y1 and yx2 is equal to y2. Okay, this is the general form of the problem. The first special case. The first special case. When x does not appear in the function f. Okay, when x does not appear in f. This means that round f over round x is equal to 0. Okay. For example, in this function y prime plus y2, okay, x does not appear explicitly. Okay, in this example, x does not appear explicitly. Okay. Now, in the first special case, round f over round x is equal to 0. Hence, if we consider the second form of Euler-Lagrange equations, which is d over dx of the function f minus y prime times round f over round y prime minus round f over round x is equal to 0, becomes this form in the first special case becomes d over dx of f minus y prime times round f over round y prime is equal to 0. Or f minus y prime times round f over round y prime is equal to a constant. This value, this function, which will be a constant. This is known as Beltrami identity. Okay, f minus y prime times round f over round y prime in this case will be constant. This constant is known as Beltrami identity. This is the first special case when x does not appear in f explicitly.
You are currently the only person in this conference.
اوکی، صدای من رو دارید الان؟ برای چند دقیقه اینترنت قطع شد، اینترنت من قطع شد. خب بحثمون در این بود که ما دو فرم برای معادله اویلر لاگرانژ داریم که این فرم بالای صفحه دی به دی ایکس روند اف روند وای پریم منهای روند اف روند وای مساوی با صفر. این میشد اولین فرم معادله اویلر لاگرانژ و این پایینی هم دی به دی ایکس اف منهای وای پریم روند اف روند وای پریم منهای روند اف روند ایکس مساوی با صفر. این هم میشه دومین فرم از معادله اویلر لاگرانژ. و داشتیم اسپیشال کیس بررسی میکردیم. اولین اسپیشال کیسمون زمانی بود که x به صورت صریح توی f ظاهر نمیشه، که x به صورت صریح در f ظاهر نمیشه. در این صورت گفتیم که روند f به روند x میشه صفر و اگر ما از دومین فرم معادله اویلر لاگرانژ استفاده بکنیم به دست میاریم نتیجه میشه که f منهای وای پریم روند اف روند وای پریم میشه کانستانت. این کانستانت صفر نیست، میتونه هر عدد ثابتی باشه. اوکی مستر مانا، this constant is not zero. This constant can be any constant number, not just zero. And it is called Beltrami identity. This constant is called Beltrami identity. اسپیشال کیس دوم، second special case دوم. When y does not appear in f explicitly. When y does not appear in f explicitly. Then we have round f over round y is equal to 0. Okay. When f does not appear in when y does not appear in f, then round f over round y is equal to 0. And if we use the first form of Euler Lagrange equation, if we use the first form of Euler Lagrange equation, okay, it will be reduces to d over dx of round f over round y prime is equal to 0, which means that round f over round y prime is a constant. This constant is not necessarily 0. It can be a constant other than 0. So when y does not appear in f, then we have round f over round y prime is a constant. و does not appear in F explicitly. In this case, y prime does not appear explicitly. Then round F over round y prime is equal to 0. And if we use the first form of Euler-Lagrange equations, if we use the first form of the Euler-Lagrange equation, it will reduces to round F over round y. This time is equal to 0, not a constant. This time, for this case, round F over round y will also be 0. Okay? Okay. حالا میتونیم وقتی که معادله اویلر لاگرانژ رو شناختیم، الان میتونیم به کمکش مثال حل بکنیم و مسئله حل بکنیم. Okay? Example number 1. Example number 1. Okay. Find the shortest smooth plane curve joining two distinct points x1, y1 and x2, y2. Find the shortest smooth plane. Last session, we derived the calculus of variation problem regarding this problem. Okay? The shortest smooth plane curve joining two distinct points x1, y1 and x2, y2. We are minimizing the arc length of the function y. Okay? This is the structure of the calculus of variation problem in this case. We should minimize Iy is equal to integral from x1 to x2, okay, of square t 1 plus dy over dx by power 2 dx. Last session we explained this problem. We explained the derivation of this problem. Okay. Now, question. Now try to answer question. Try to answer my question. Which special case appears in this problem? We explained 3 special cases. Okay? We explained 3 special cases. Which is a special case appear in this problem? Okay, Mr. Mana. This is the second special case, which means that y is not in F. Okay. In this problem, the function y does not appear explicitly. So according to the second special case, when y does not appear in F explicitly, then the Euler Lagrange would be round F over round y prime is equal to constant. Okay? In the second special case, the Euler Lagrange equation will be round F over round y prime is equal to constant. Okay? Therefore, here we can write round F over round y prime is equal to y prime over the square root of 1 plus y prime by power 2. And according to the second special case, we have that y prime over the square root of 1 plus y prime by power 2 is a constant, is equal to a constant C. This result is obtained according to the second special case. Now, this is a differential equation. Okay? This is a differential equation. By solving this differential equation, we can obtain the solution y. By solving this differential equation, we can obtain the solution y. Now, let's check the solution. We have that y prime is equal to C times the square root of 1 plus y prime by power 2. Okay, so y prime by power 2 is equal to C by power 2 times 1 plus y prime by power 2, or y prime squared. Which means that y prime squared minus C squared y prime squared is equal to C squared. Hence, 1 minus C squared times y prime squared is equal to C squared. Consequently, we can easily obtain that y prime squared is equal to C squared over 1 minus C squared. Okay? Which means that y prime is equal to square root C squared over 1 minus C squared. Let this value be m. Okay? We suppose that this value is m for simplicity. Okay? For simplicity, we assume that this value is m. Now, y when y prime, when y prime is equal to m, then y would be mx plus b. Okay? When y prime is equal to m, then y would be mx plus b. Okay? Now, if we use the boundary conditions, if we use the boundary conditions, the values of m and b can be obtained. Okay? Using the boundary conditions, the values of m and b can be obtained. Thus, the curve having minimum arc length passing through the given two fixed points is a straight line. Okay? The answer is simple. The answer to this question is simple. But in this example, we tried to obtain the solution using Euler-Lagrange equations. Before solving this problem, we already know that the solution is a straight line. Okay? A curve having minimum arc length passing through the given two fixed points is simply a straight line. But in this example, we prove using the Euler-Lagrange equations that the solution is a straight line. خب پس در این مثال، در مثال example number 1 ما یاد گرفتیم که اگر یک مسئله مینیموم سازی فانکشنال داشته باشیم، اکسترمایز یک فانکشنال رو بخوایم به دست بیاریم، از معادله اویلر لاگرانژ استفاده میکنیم. اگر یکی از این سه تا اسپیشال کیس بود، اسپیشال کیس خودش رو، یعنی فرمول مربوط به اون اسپیشال کیس رو استفاده میکنیم. اگر اسپیشال کیس نبود، یکی از دوتا فرم معادل اویلر لاگرانژ رو به دلخواه میتونیم استفاده بکنیم. در هر صورت معادله اویلر لاگرانژ برای ما یک معادله دیفرانسیل تولید میکنه. در هر صورت معادله اویلر لاگرانژ یک معادله دیفرانسیل تولید میکنه و با حل کردن این معادله دیفرانسیل میتونیم جواب وای رو به دست بیاریم. Okay. Exercise. Show that another form of Euler-Lagrange equation is round f over round y minus round f of y prime x minus round f of y prime y times y prime minus round fy prime y prime times y is equal to 0. This is another form of the Lagrange equation. This form is also important. Okay. Example number 2. Example number 2. Find the extremals of the functional integral from x0 to x1 of y prime squared over x cubed dx. Okay. In this example, we have another functional. And we must obtain its extremals. Okay. خب توی این مثال ما تابع f رو به این صورت داریم. تابع f مون مساوی با y پریم به توان 2 تقسیم بر x به توان 3. پس گام اول اینه که تابع f رو تشخیص بدیم. y پریم به توان 2 تقسیم بر x به توان. Which special case is this example? Which special case? No, this is not the third special case. Yes. The special case 2. Okay. Also 2. In this example, we have round f over round y is equal to 0. بنابراین روند f به روند y پریم رو به دست میاریم. روند f به روند y پریم میشه 2 تا y پریم تقسیم بر x3. اوکی. 2 تا y پریم تقسیم بر x3. حالا جایگذاری میکنیم در معادله اویلر لاگرانژ. اوکی. در معادله اویلر لاگرانژ جایگذاری میکنیم و به اینجا میرسیم که 2 روی x4 در xy زگم منهای 3y پریم مساویه با 0. از این چه نتیجه میشه؟ نتیجه که از این میگیریم اینه که xy زگم منهای 3y پریم باید 0 باشه. اوکی. xy زگم منهای 3y پریم مساویه با 0. خب بازنویسیش به این صورته: y زگم تقسیم بر y پریم مساویه 3 تقسیم بر x. حالا اینو انتگرال میگیریم. integrating from both sides. از طرفین انتگرال میگیریم. integrating from both sides. از طرفین انتگرال میگیریم. انتگرال y زگم تقسیم بر y پریم مساوی با 3 تا انتگرال 1 x dx به اضافه c. c اینجا ثابت انتگرال گیریه. Okay. Here c is the constant of integrating. c is the constant of integrating. سمت چپ انتگرال y زگم تقسیم بر y پریم میشه ln y پریم. انتگرال y زگم تقسیم بر y پریم میشه ln y پریم. 3 تا انتگرال 1 x dx هم میشه 3 تا ln x به اضافه c. در نتیجه hence ln y پریم تقسیم بر x3 مساوی با c میشه. ln y پریم تقسیم بر x3 مساوی با c or y پریم is equal to c x cubed. y پریم مساوی با c x به توان 3. و از اینجا هم با یک انتگرال ساده میتونیم y رو به دست بیاریم. y میشه cx4 تقسیم بر 4 به اضافه c2. یا اگه بازنویسیش بکنیم y مساوی میشه با ax4 به اضافه b. اینجا a مساوی میشه با c4 b هم مساوی با همین c2. پس تو این حالت هم تو این مسئله هم جواب رو تونستیم به دست بریم. برای این فانکشنال که مدده شده the solution will be y is equal to a x by power 4 plus b. خب حل رو تکرار میکنیم دوباره. تنظیمات صفحه من ریخته به هم. خب صدای من هست الان؟ صدای من رو دارید؟ اوکی اوکی. خب این اگزمپل تو رو توضیح دادم، ولی میتونیم به صورت ساده تری هم حلش بکنیم. We already explained example number 2, but we can solve it in a simpler form. Okay? How to solve it in a simple form. گفتیم این مسئله کیس شماره 2، اسپیشال کیس نمبر 2. خب بر طبق اسپیشال کیس نمبر 2 باید روند F به روند Y پرایم مساوی با ثابت باشه. کانستانت K باید باشه. خب تو این مثال نتیجه میشه که تو Y پرایم تقسیم بر X مساوی با ثابت K. در نتیجه Y پرایم میشه K تقسیم بر 2 ضرب در X. بنابراین Y مساوی میشه با A تقسیم بر 2 از در X4 به اضافه یه ثابت انتگرالگیری C. خب این تکنیک دیگه هست که ما میتونیم راحت‌تر جواب به دست بیاریم. اگر از اسپیشال کیس 2 استفاده بکنیم If we use the second special case, we can obtain the solution easily. اگر از اسپیشال کیس شماره 2 استفاده بکنیم جواب رو میتونیم راحت تر به دست بیاریم نسبت به اون چیزی که توی جزوه میبینید. Okay? Any question? خب example 3. Example number 3. Extremize Iy is equal to integral from x1 to x2 1 plus y prime squared dx with the boundary conditions yx1 is equal to yx2 is equal to 0. Okay. We should solve this problem, this calculus of variation problems. Again, in this example, we have f is equal to 1 plus y prime squared, and round f over round y prime is equal to 2y prime. Okay, so similarly to example number 2, we have d over dx of 2y prime is equal to 0. So 2y is equal to 0, which means that y prime of x is equal to c, and yx is equal to 6 plus d. Okay? And based on the given boundary conditions, we can obtain the value of c. So the third example is also very simple. Example number 4. Example 4. Find the curve y on which the functional integral from 0 to 1 of y prime squared plus 12xy dx with the conditions y0 is 0 and y1 is 1 is extremum. Okay. are going to solve this calculus of variation problem. Integral from 0 to 1 of y prime squared plus 12x y dx subject to boundary conditions y0 is equal to 0 and y1 is equal to 1. Try to answer my question. Which special case is appeared in this example? Which special case? No. Number 3. Special case number 3 is that y zegom is not appeared. Okay. Here you can see y prime is appeared in F. F is equal to y prime squared plus 12xy. No special case. Okay? No special case. Wait a moment. Okay. Here we have no special case because x, y, and y prime are appear explicitly in F. Because x, y, and y prime are appear explicitly in F, we have no special case in this example. Okay, let me check the solution. As I told you, here we have f is equal to y prime squared plus 12xy. Okay, so According to Euler-Lagrange equations, we have 12x minus 2y is equal to 0, or y is equal to 6x. Okay, according to Euler-Lagrange equation, we have y is equal to 6x, which means that y prime is equal to 3x squared plus c. Okay, y prime is equal to 3x squared plus c, and y is equal to x cubed plus cx plus c prime. Okay, now applying the conditions. What was the conditions? We have y0 is equal to 0, and y1 is equal to 1. Okay, so applying the conditions, we get y is equal to x cubed and the solution of example number 4 is also obtained. Any question? Okay. About exercise. What is it? Exercise. Let me explain. Okay. Okay, Mr. Mana. On page 7, we introduce a theorem that gives us the first form of the Euler-Lagrange equation. Okay. This is the first form of the Euler-Lagrange equation. And as I told you, try to understand the proof of this theorem. Okay? Read this proof and try to understand it. So, on page 9, on the top of the page 9, we have the first form of Euler-Lagrange equation. And here we have different forms of Euler-Lagrange equations. We prove that on page 9, we obtained the second form of Euler-Lagrange equation. This is the proof of second form of Euler-Lagrange equation. Okay. Now, try to use the information on page 9. Try to use the information on page 9 and obtain the third form. This is the third form of Euler-Lagrange equation. Okay? Now, try to use the information on page 9. Try to use the information on page 9 and obtain the third form. This is the third form of Euler-Lagrange equation. Okay? Use the information on page 8 and 9. Okay, 7 and 9. Use the information on page 7 and 9 to obtain the third form of the Euler-Lagrange equation. This is exercise on page 11. Okay? Okay, so for this example, use the information in page 7 and 9. Okay. Let's also check the next problem. Okay. Which is the shortest time of descent problem. This is a very famous problem. This is a very famous problem in calculus of variations. Shortest time of descent problem, which is also called Brachistotron problem. Okay, Brachistotron is a word from Greece. Okay, Brachistotron is a word from Greek. Shortest time of descent problem. This is very famous problem in calculus of variation. what is the problem? Find, okay, pay attention, find the shortest path, on which a particle in the absence of friction, okay, in the absence of friction will slide from one point to another point, okay. Will slide from one point, okay, from point O to point P1. Okay. A particle in the absence of friction will slide from one point, which is point O, to another point, which is point P1, in the shortest time. In the shortest time. Okay. In the first view, okay, in the first view, the solution may be a straight line. Okay. In the first view, the solution may be a straight line, but we will observe that the solution is something different than a line. The solution is not a straight line. The solution is a special curve, as you can see in the figure. Okay? The solution of shortest path in the shortest time. Okay? Shortest path in the shortest time will be a special curve, not a straight line. Now let's check the solution. Let the particle slide from O along the path OP1. Okay? Look at the figure. Let the particle slide from O along the path OP1. Let, at time t, the particle be at pxy. Okay? At time t, the particle be at pxy, and let arc of OP be s. Okay? Arc of OP be s. Here we are explaining the derivation of this problem. Okay? According to some physics rules, we are explaining the derivation of this problem. By the principle of work and energy, we have Ke at P minus Ke, okay, at O, okay, work done in moving the particle from O to P. So, we have that 1/2 times m times ds/dt squared, okay, minus 0 is equal to mgy. So, what is m? M is the mass of the particle. Okay? M is the mass of the particle. جرم اون ذرمون پارتیکلمون برابر با M. G is gravity. Okay? G is gravity and Y is the curve. Okay? Y is the curve that shows the shortest time. Therefore, we have that ds over dt is equal to square t to gy. Okay. Now, time taken by the particle to move from O to P1, time taken by the particle to move from O to P1 is given by T is equal to integral from 0 to T of dt. Okay, which is integral from 0 to x1 of ds over square T of 2gy, which is equal to 1 over 2g integral from 0 to x1 of square T1 plus y prime squared over square T of y dx. Therefore, we can write that T is equal to 1 over square T of 2g. G is the gravity of the Earth. Times integral of 0 to x1 of square T of 1 plus y prime squared over square root of y dx. This is the time taken by the particle to move from O to P1. Now, the Brachistotron problem, or the shortest time path. Brachistotron problem, or the shortest time path, is to find y. The problem is to find y, which minimizes the function of iy is equal to 1 over square root of 2j integral from 0 to x1 of the given function f. This is the structure of the Brachistotron problem. We have to minimize this functional. In the Brachistotron problem, we have to minimize this functional with the given function f. Okay, with the given function f. Now, let me check its solution. Okay, the derivation of the problem has completed. Now let we check its solution. Since x does not appear in f explicitly, take the Beltrami identity. Okay, so this problem is the special case 1. the Lagrange structure of our problem is a special case 1. And we can take the Bertrami identity. So, according to the special case 1, we have that f minus y prime times round f over round y prime is equal to a constant. So, let me substitute f and round f over round y prime. Okay. If we substitute f and round f over round y prime, we obtain the second line. Okay. We obtain the second line. And after that, we try to simplify it. After that, we try to simplify it in the third line. And hence we obtain in the fourth line, we obtain 1 plus y prime squared minus y prime squared over the square root of y times the square root of y plus y prime squared is equal to c. Okay. Therefore, we have this equality. Okay. We have this equality, which means that the square root of y times 1 plus y prime squared is equal to 1 over c. This part is an assumption. This part is our assumption. We assume that 1 over c can be written in the form square root of a. Okay. We assume that 1 over c can be written in the form square root of a, and this assumption is just for simplification. This assumption is just for simplification. So, by this assumption and for simplicity, we obtain y times 1 plus y prime squared is equal to a. Okay. This simplify equations very much. Therefore, 1 plus y prime squared is equal to a over y, and y prime squared is equal to a minus y over y. So, y prime is equal to square root of a minus y over y, and dy over dx. Y prime is, you know that, is dy over dx, is the square root of a minus y over y. Therefore, we can write a square root of y over a minus y dy is equal to dx by integrating of both sides. By integrating of both sides, we have integral of from 0 to x of dx is equal to integral from 0 to y of the square root of y over a minus y dy. Next, since the point 0 and 0 is point on the curve, we get c is equal to 0. The origin, the point 0 and 0 is the point of the on the curve. We get c is equal to 0. So y would be a sine squared of theta. Okay, y would be a sine squared of theta, and dy would be 2a sine of theta cosine of theta d theta. Thus, x would be integral from 0 to theta of the square root of a's sine squared of theta over a minus a times sine squared of theta times 2a sine of theta cosine of theta d theta. Now we simplify the function in the integral. We first simplify the function in the integral. So we obtain x is equal to integral from 0 to theta of sine of theta over cosine of theta times 2a times sine of theta times cosine of theta d theta. After simplification, we obtain a integral from 0 to theta 2 sine squared of theta d theta, which is a integral from 0 to theta of 1 minus cosine of 2 theta d theta, and we can easily obtain x. Finally, let a over 2 be b and 2 theta be phi. Okay? Let a over 2 be b and 2 theta be phi. Then, by substituting in x and y, we can obtain the solution. Okay? So the solution would be x is equal to b times phi minus sine of phi, and y would be b times 1 minus cosine of theta. This solution is called cycloid. This solution is called cycloid. The plot of this cycloid, is something like this figure. Okay? In this figure, you can observe the plot of the given cycloid. So this solution shows that the shortest time curve is not a straight line. Okay? The shortest time curve is a cycloid, not a straight line. page 14. Okay. For the next session, remember me to continue from page 14. Okay. For the next session, remember to continue from page 14. Okay, this session has finished. Any question?